So continuing in Unit 5, we're now going to look at a special type of discrete probability distribution called the binomial probability distribution. So when we look at the binomial distribution, it is simply a special type of discrete distribution. And we also will again look at interpreting those unusual, really high or really low values. So in the discrete distribution, we have a fixed number of trials. N is our number of trials that are going to be attempted. Next, the number of trials, the trials themselves must be independent. What that means is the results of one trial cannot change the results of another trial. If we were looking at like marbles out of the box, that would mean we'd have to be doing this with replacement and things like that. Next, all of the outcomes must be able to be classified into two categories, success and failure. That doesn't mean there's only two outcomes, that means they're classified into two categories. For example, rolling a die. There are 6 possible outcomes there, but maybe we say that getting a 1 or a 2 is a success and anything else is a failure. Now we've classified them in those two categories. And finally, the probability of success has to be the same on all of the trials. It cannot change over time. If we're rolling the die, as long as the die stays undamaged, the probability of getting a 1 or a 2 stays the same, no matter what, unless if we chip the die or something like that, or we change to a different die, then we would have to start over. It would no longer necessarily be exactly the same anymore. So our notation here, I already mentioned N is the number of trials we're going to do. P is the probability of success on one of those trials. And then some textbooks just use 1 minus P. This textbook defines it as Q is equal to 1 minus P. That's the probability of failing on a given trial. Then also we're going to use X as our random variable. That is the number of successes out of those N trials. So again, as we're looking at this, X, the number of successes, P, probability of success on each trial, Q, the probability of failure. P of X is the probability of getting a certain value of X, a certain number of successes out of those N trials. And so that's what we're going to be looking to calculate here. By the way, the possible values of X would go from 0 on up to N. We could have no successful trials, or we could have all of them as successful trials. A note here, the word success, we're used to it being a good thing, but it isn't necessarily. Success just means the thing that we were looking to find the probability of happened. It could be a very bad thing, it could be a disastrous thing. It's just it was the successful result in terms of what we're looking at is having the result we were looking for, not necessarily a good result. Also then, when we look at calculating our binomial probabilities, we need to make sure that X, the random variable, what we're looking for, and P, the probability of a success, are representing the same thing. For example, we might say 1 out of 4 students, the probability of a randomly selected student having their laptop with them to class is 0.25. And then we might ask if out of 10 randomly selected students, what's the probability that 8 of them do not have their laptops with? Well, that's asking for different things. The 0.25 was the probability that they had their laptop, and now we're asking how many don't have their laptop. So we got to make sure we're being consistent when we're asking that the number that we're asking for X is represented by the probability P, the success. So here's our example here. When an adult smartphone owner is randomly selected with replacement, so that way we're guaranteeing that the probability of success stays the same from one trial to the next. There's a 0.05 probability that this person is what we call cashless. They don't carry cash. They use all credit card or they use phone pay of some sort. Of course, 2003 phone pay was not a big thing at that point. They don't carry cash on them. We want to find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. So n equals 10. We're selecting 10 adults. That means we're taking 10 trials. 2 of them are cashless. So that's x equals 2. And p is the probability of success on a single trial. That's 0.05. Each person has a 0.05 probability of being cashless. Yes, this is a binomial distribution, especially the fact that we said with replacement means that p is going to stay the same. If this procedure is binomial, we've identified nxpq, then of course would be 1 minus p, so 0.95 would be q. So that they just go through our answers. There's a number of trials. N is 10. They are independent because it is done with replacement. And the probability of one does not affect the result of another. They are divided into 2 categories, success and failure. If they're cashless, that's going to be a success. If they're not, that's a failure. Cashless is not necessarily a good or a bad thing. It's just that's the characteristic we were looking for. That's why it's called success. And that probability of success on individual trial is 0.05, and it stays 0.05. So now, let's find the probability that exactly 2 of them are cashless. So our probability of success, as we said, was 0.05, failure 0.95. Our notation is consistent. P represents the probability of being cashless, and we're trying to find the probability that 2 out of the 10 were cashless. So we've guaranteed that we've met that condition as well. 5% guideline. Now, we did this with replacement, but we could have done it without replacement. As long as the amount of people we're choosing, the size of our sample, is less than 5% of the whole population, we could make the assumption that they are independent. Even though the probability might change slightly with that small of a sample compared to the size of the whole population, the probabilities would not change significantly. So that is we call that the guideline for cumbersome calculations. It allows us to simplify those calculations rather than having to adjust the probability after each item drawn when there's no replacement. We can assume that they're independent. So our formula for binomial probabilities is the probability of getting x successes out of n trials is n factorial over n minus x factorial and x factorial. P is the probability of success on an individual trial to the power of x, which is our number of successes, times q, which is the probability of failure on an individual trial, to the power of n minus x, which is the number of failures. So for this, of course, n is 10, x was 2, so that would be 8 factorial, and then again 2 factorial. P was 0.05 to the power of 2, because we're expecting 2 successes. Q is 0.95 to the power of 8. 10 minus 2 would be 8 failures. And we would calculate all those and multiply them together. So this is just reviewing our values for each of those variables before we plug them in to our formula, and here we go. So plugging them all in just as I did in that previous page, we get a 0.074 probability. So I'd show you how to punch those into a calculator. If you have a factorial button on your calculator, and if you have a scientific calculator, you do have a factorial button. Mine is hidden in the math screen, so I would enter 10. I'd go to math, probability, factorial is option 4. That gives me my factorial. Divided by, now I have to put parentheses on bottom here in a couple of places. So I do 2 parentheses, then it's the 10 minus 2, close my parentheses and put in a factorial, times 2 factorial again. Then I close my parentheses for the bottom of that fraction. Times the 0.05 to the power of 2 times, I'm in parentheses, 1 minus the 0.05 or the 0.95 to the power of 10 minus 2, or 8 failures. Giving us now, this is giving us a, oops, did I get a factorial? I got a 12 got put in there instead of a 10. Let me get that corrected. There we go. So we get the 0.07463, just like the slide shows us. Now this number, what it shows up here, the 8.29, that's not a legitimate probability. You can have a probability bigger than 1, but you see over here it's e negative 4. That's scientific notation. So that's saying times 10 to the negative 4th. So that'd be saying that decimal point would have to move 4 spots to the left. So what that's really trying to say is 0.000829 probability. So if you see that pop up on your calculator of e negative 4, remember that is scientific notation. You have to make that conversion in order to report your answer. So that's the probability that exactly 2 are cashless. Now, many of you do not have a graphing calculator. We do all have access to Excel. So let's go to Excel and look at how we would do this calculation. So in Excel, we use the command, we do equals, and then binom.dist. Now, depending if your Excel is set up to give you these little hints, if you do the open parentheses, notice it tells us what we want. Number of successes, well, that was 2, comma, number of trials, that was 10. Probability is the probability of success on each trial, that's 0.05. And then cumulative, we're going to say false. We do not want it cumulative. False means we just want the value, the probability for that value of 2. If we said cumulative, that would be asking for the probability of being less than or equal to 2. So that would be adding up 0 up through 2. We just want the single probability. And there we get the probability that we had. Well, since we're here, let's make a probability distribution for this. X and P of X. Remember, X can go from 0 all the way up to 10. And so this will equal binom.dist, open parentheses. I'm going to click here because that's the number of trials, or number of successes, comma, 10 trials, 0.05 probability, and false. And then we go down. So notice the most likely outcome is to have 0 people cashless. You'll notice again that we have this scientific notation here. I'm going to just do this one. This is saying times 10 to the negative 5, which means move the decimal point over 5 spots. So that's saying 0.0000609. Now when I hit enter, it's going to leave that one as it is rather than put it in scientific notation. But that's what that means. Those are the same number. Now let's just double check to make sure this is valid. I'm going to do the total here. These should add up to, remember it should add up to 1. And it does. It adds up to exactly 1, which is perfect. Now, if I want to do probabilities, I can just add up probabilities from this table in order to get probabilities for different values or ranges. Or we can learn how to use the cumulative probability function coming up here in just a few minutes. So the slides do cover using Excel for these. They actually use a little bit different way of doing it rather than just typing it in directly, and I'll show you how that works. Let's say I wanted to type this in. What I could do when I enter binom dist, first I can select it from here, and rather than using these hints here that tell me what it's looking for, I can actually click on f of x here, and it'll bring up an input box. So it asks number of trials. Well, that's where I clicked on this. Or sorry, number of successes. That's where I clicked on that. Number of trials, I entered in the 10. Probability of, oops, I hit enter too soon. Probability of success is 0.05, and cumulative is false. Then I hit enter, and it gives me the same thing. All it is just a different way of entering these numbers into the formula by using the box that tells us what each item is. You notice these items here are exactly the same as what's listed here. It's just whatever way you prefer seeing it, pretty much. And you can see those are the exact same numbers we got when we pulled them up in Excel too. So anyway, let's look at the football overtime rule and do an example there. We previously noted that between 1974 and 2011, there were 460 NFL football games decided by overtime. 252 of them were won by the team that won the coin toss. So is winning a coin toss give you an unfair advantage in overtime? Is the 252 wins out of 460 a significantly high number? So we'll use our notation. N is our number of trials. That's 460 because there's 460 games. We would expect the probability of winning to be 0.5. So then Q, the probability of losing, would be 0.5 as well. So our probability of success, that's the probability of winning, is 0.5. Probability of failure, which is losing, is 0.05. And we're looking at the probability of winning 252 or more. So we could go into Excel here. I'll go to a new page, and we could number 0 through 252. Actually, 0 through 460, I should say. It's going to take a while just to scroll down that far. And then we could find our probability. So equals binomial dist. So our number of successes is this value from here. Number of trials is 460. Probability of success, we're going for 0.5. And cumulative, no. Now notice that's e to the negative 139. That's a really small probability. But remember, there's 460 values here, and they do all have to add up to 1. So we get all those probabilities. Again, really small probabilities. The sum, the total here, though, they do add up to 1. Well, we wanted to know if 252 was an unusually high amount. So we want the probability of winning 252 or more. So I'm going to do this. I'm going to do equals sum. I'm going to add up from 460, and I'm going to go up to 252. Let's look at what that total came out to be. Came out to 0.022. That's a pretty small percent probability. Let's see if we match up the results we got up here. So they're going to use Excel as well to calculate this probability, but rather than using the table, they're going to use the cumulative function. Now we saw here, 460 items. We had to go up, 461 rows to get that done. It's way easier to use the cumulative function. So if I put in true instead of false, in this, so let's say I'm going 251 out of 460 trials with a 0.5 probability, and I'm going to put in true instead of false. So when I said false, I was saying I just want the probability of this single value. Well, that's going to be really small when there's 460 different values. When I say true, I'm saying I want the probability of being less than or equal to this. That's the reason I put in 251 instead of 252. This is the probability of being 251 or less. So probability that x is less than or equal to 251. So then the probability that x is greater than or equal to 252, which is the complement, is just going to equal 1 minus that probability, or the 0.224 is what we found down below. And so as they go through this, again, they're using that complement just like we did. They found that being 251 or fewer, using that cumulative function, gave them the 0.978. They did 1 minus 0.978 to get the 0.022, which is what we found. This is less, so this is the function they used, what we entered as well. That is less than 0.05. So that's saying that that is a small amount, an unusually small amount. So it is a significant amount. If you don't have technology, you can always use the table in the appendices. I'm not going to go over the appendix table because we all have Excel available. So we are not going to use that function. Especially when there's 460 items available. The table in the appendix does not go up to an n of 460 anyway. So here's another example based on a Gallup poll. 5% of adults are vegetarians. We randomly select 5 adults. So n equals 5. P equals 0.05. That's for the 5%. Probability that exactly 2 of the 5 are vegetarians. That's x equals 2. But probably there are fewer than 3. So that's the probability that x is less than 3, which is the same as the probability that x is less than or equal to 2. Because both of those are saying the probability of 0 plus the probability of 1 plus the probability of 2. Because this, remember, does not include the 3 when it's strictly less than. So we go to a table where n equals 5 and find the probabilities for p of 0.05 and x of 0, 1, or 2 and add them up. Or I can go to Excel here. I'll go to a new page since it's a new problem. Equals binomial dist. Oops. Select my function, then hit f of x. Now our number of successes, we want to go up to 2. I just type in the 2. Trials is 5. 0.05 was 5%, and this is true. We want this to be cumulative, 0, 1, or 2. So we get 0.9988 is the chances of having 2 or less than 3 people be vegetarians. And of course that adds up 0.999 if they round off to 3 decimal places. When we're looking at a binomial distribution, the mean of the binomial distribution is n times p. Number of trials times the probability of success on a given trial. So like for our example with vegetarians, it's 5 for n times 0.05 gives us 0.25. What that is saying is, on average, we would expect 0.25 people out of 5 to be vegetarians. That's a pretty small amount. The variance is then n times p times q. So that's 5 times 0.05 times 0.95. So that would be 5 times 0.05 times 0.95, 0.2375. And then, of course, the standard deviation is the square root of that. We just take the square root of that answer. We get 0.4873. And of course, the slide's going to round off to a little bit smaller amounts than that if they do it. The rule of thumb again for our range, significant low values are more than 2 standard deviations below the mean. Significantly high values are more than 2 standard deviations above the mean. So if we look at this example here of those 460 NFL games, we said the probability of winning of 252 of the people who won the coin toss winning the game was a significantly small probability. So let's take a look at using the rule of thumb here. So our mean out of 460, that would be 0.5 times 460, or giving us 230 is our mean. We would expect 230 out of the 460 games to be won by the team who won the coin toss. Standard deviation then is n times p times q, and then square root that. So that's the square root of 115, giving us 10.7 is the standard deviation. So from the mean, an unusually small amount would be 230 minus 2 times 10.7 would be 21.4, which is 208.6. So if the team that won the coin toss won less than 208 of those games, that would be a significantly small amount. The 230 mean plus the 21.4 is 251.4. If the team winning the coin toss won more than 251 of those games, we consider that to be a significantly large amount. Well, so 252 is just slightly more than that. So it is a significantly large amount. So we're saying that, yeah, it's a significant advantage to win the coin toss. And that's the analysis that the NFL did. That's why they changed the rules so that it's no longer just the first team to score that wins. And that's just going over that analysis saying that 252 is a significantly large number because it's more than 251.4. So this is one of the ways we can use our probabilities to decide if a value is significantly high or significantly low. Remember, if its probability of being that small is less than 0.05, then it's a significantly low number. Or the probability of being that large, which is the case in the overtime football games, is less than 0.05, that's a significantly high number. So the binomial theorem, we already kind of went through the binomial formula a little bit. This is the number of ways we can have that many successes out of our number of trials. This is the number of successes or the probability of a success on an individual trial to the power of the number of successes. This is the probability of failure on the individual trial to the power of the number of failures. So that is the binomial rule. Get good at using Excel. If you do have access to a TI-84 calculator, the one I have on screen here is actually just a TI-83. The TI-84 has a couple extra functions in it that are helpful later on. If you have access to it, it is a great tool for the binomial calculations, like the less than 251, you would have done second. Distribution. Binomial is down here a ways. Binomial PDF, that would be the binomial false. Binomial CDF would be the binomial true. That's the cumulative. So I want the binomial CDF, 460 trials, comma, 0.05 is my probability of success, comma, oops, not 0.05, 0.5 is my probability of success. And I want to know 251 or less. That gives me that same 0.978 probability that we subtract from 1 to get 0.022 is what we found in our NFL example. If you do have access to the TI-84 calculator, let me know, and I can post some videos for you on doing binomial probabilities with the calculator later. So that is the end of Unit 5. Let me know if you have any questions.